Now, when we were looking at Hamilton paths and circuits, we had said that there's going to be no easy algorithm to determine whether or not a graph has one. You're just going to have to take a look at the graph and see if you can locate one. We're going to take a look at a very special type of graph that will always have a Hamilton circuit, which is known as a complete graph. And the other cool thing about this is that every traveling salesman problem can be represented by a complete graph. So a complete graph is defined as a graph that has exactly one edge between each pair of vertices. No more, no less. So every vertex is connected by one edge. We're going to use little n to designate the number of vertices. Okay, so right here is a complete graph with 3 vertices. Here's a complete graph with 4 vertices, 5, and then 6. So notice that we tend to put the vertices kind of in a circular pattern. It just helps because every vertex has a connection to every other vertex. There's typically a lot of edges in these graphs, so this kind of just keeps everything organized and kind of spatially similar to each other. So every traveling salesman problem can be represented by a complete graph. Now, one of the things that we're going to be looking for in these types of graphs are how many different unique Hamilton circuits are possible. So there's going to be a formula that's going to help out with that. The number of unique Hamilton circuits in a complete graph with n vertices is given by the formula of n minus 1 and then factorial. So this exclamation point thing right here is a factorial. And what it represents is multiplication of the number that would be sitting right here down to the number 1. So as an example, 5 factorial would be the evaluation of 5 times 4 times 3 times 2 times 1. Okay, so you would start with whatever number you're seeing right here, and you're just going to go down by 1 until you get down to the number 1, and you multiply all that stuff together. Most scientific and graphing calculators have a factorial button, so you don't have to key in all this multiplication by hand. So I have a graphing calculator where I'm going to show you where the factorial is. If you have a scientific calculator, you may need to refer to the owner's manual to find out where your factorial key is. So you would key in your 5, and then in this calculator I'm going to go into Math. Then I'm going to arrow over to the PRB menu, and then I want option 4 as my factorial. So you can either arrow down to the number 4 and hit enter, or I can just key in the number 4 to grab it. So this is going to be 5 factorial, so I'll hit enter, and then this would give me 120. Okay, so you should know where the factorial key is on your calculator, just so that way you don't have to key in all that multiplication by hand. Now when we go to talk about the number of unique Hamilton circuits, let's take a look at what we are counting here. So here is some copies I have of a complete graph with 4 vertices. So this formula tells us then I would have 4 minus 1 factorial, or 3 factorial, or 3 times 2 times 1, or 6 unique Hamilton circuits. And I have already prepared for us 6 copies of this complete graph. We're going to go ahead and record what each of these different Hamilton circuits look like. Now, to be consistent, for every one of these, I'm going to start at A. So we had talked in this previous example, so I'll come up here. We had said that staggering the starting vertex does not count as a different circuit. So one of the things that we would do when we want to do this counting argument is we're going to lock in that starting vertex, and then we're going to keep track of the direction, because the direction that you go from that starting vertex will matter. So coming back down here then, on all these I'm going to start at A. So I could go from A to B to C to D and then back to A. There's a Hamilton circuit. Now, we had said that the direction matters, so if I went from A to D instead, and then to C, then to B, and then to A, we're going to count that as a different Hamilton circuit. Even though this grabs the same edges, I'm going through those edges in a different order. Okay, so let's find a different one. So as a reminder, I will refer to these two as mirror images. It grabs the same edges, but it just goes about them in a different order. So how about something totally different? How about from A, I will still go to B, but now as opposed to going to C, how about I pop over here to D? From D, I'll go to C, and then from C, we'll go back to A. Okay, so there will be a new Hamilton circuit, and then I could have that exact same pattern, but I could go the opposite way. So I could go from A to C. So I'm basically going to start reading this in reverse order. Then to D, then to B, and then finally back to A. So there's two more that are also mirror images of each other. And then finally, as from A, I could go to, for instance, let's see, we've gone from A to B, I've gone over here from A to D. How about from A to C? We haven't done that yet. And maybe from C I go up to B. And from B I'll go to D. And then from D I'll come back to A. So it's kind of like a bow tie going the other way. And then again, I could have that in reverse order. So I could have from A to D, then up to B, then down to C, and then back to A. So there are your 6 unique Hamilton circuits. Okay, so one way to maybe remember what's going on here is, remember, we're going to lock in that starting vertex. So on all of these, I said I'm going to go ahead and start at A. Now I have to go to all the other vertices in the graph, so I have 4 vertices, and then I'm going to have to come back to A. Okay, so another way to remember this counting argument is said, okay, so if I'm going to start and end at A, I only have one choice there. Now here, for my second vertex, I had choices of either going to B, C, or D. So I had 3 choices there. So I would have to pick one of them. Once I chose one of those vertices, I can't come back to it. So then for the next vertex I can go to, I would only have 2 choices there, and then finally 1 choice for that third vertex. So then we can multiply all these numbers together, and there's another way we can get our 6 possible circuits. Extending this idea, let's take a look at these examples. So we're going to consider a traveling salesman problem with 11 vertices that are going to be labeled A through K. So how many circuits are there of the form? We'll start at A and then we have to go to B. Now this n-1 factorial formula won't apply here because there are additional restrictions on where I can go. So here's where I'm going to have 11 vertices, so maybe I'll put down 11 blanks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then I got to come back home. Let's go ahead and figure out how many possible circuits I can get here. Now at this point in time, I have to start at A. So there's 1 possibility there, and I have to go to B next. So there's only 1 possibility there. Now here's where I'm going to have all the other vertices I have to go to, and then I have to come back to A. So again, there's only going to be 1 possibility there. So at this point in time then, for this next vertex, what do you have left here? Well, you would have C, D, E, F, G, H, I, J, or K, right, as your next possibilities, because you can't go to A and you've already gone to B. So how many options do I have right here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Or you can say, since you have 11 vertices total, you've used up 2 of them already, you would have 9 left. So you would have to make a choice there. And then we're going to have 8, then 7. So we're just going to keep losing a vertex all the way down the line. 3, 2, and 1. All right, so this will be all of these other letters, using up each one of them as we go. And then, so this will start at A, go to B, then this is where I kind of have my flexibility, and then we'll go back to A. So to evaluate this, I would need to figure out what the value is for 9 factorial is. Now in your calculator, you could key in 9 times 8 times 7 times 6, etc. Or you can go into your calculator's functions and grab that factorial button. Either way, you should get that there are 362,880 possible circuits. So that's a lot of circuits. So in this next example, it says how many circuits are of the form D, then B, and then go through all of them. Then you have to go to K before you come back home. So again, I'm going to put down my blanks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's for my 11 vertices, and then I got to put down one more to come back home. So this says I have to go to D, maybe I'll put these down here, D and then B. Okay, so there's one option for each of those guys. And then I have to go to K before coming back home. So there's one more option here, and then one option there. All right, so who do I have available here? Well, at this point in time, out of my 11 vertices, I have used up 1, 2, 3 of them. Right, the starting vertex and then B and K have already been used up. So here you have A, can't go to B, you've got C, E, well, can't go to D. So then we're going to have F, G, H, I, J. Okay, so you would have 8 options for this vertex right here. And then again, we're just going to lose one all the way down. So 7, 6, 5, 4, 3, 2, and then, oh, made a mistake right there. 3, then 2, then 1. That looks a little bit better. All right, so then we would just multiply all these together. So then you can see then really what we're going to have to compute here is going to be 8 factorial, which if you key that in your calculator, you should get 40,320 possible circuits. Okay, so we can use these counting arguments to be able to figure out how many circuits that we have. So the n-1 factorial formula will not apply if there's additional restrictions on what vertices, for instance, you can start at the beginning, or where you have to go before you come back home, or maybe there's going to be some restrictions on where you have to go in the middle. Okay, so you can use these types of generic counting arguments.